Today we'll be starting chapter 4, which is on differentiation rules. You've noticed that taking a derivative by definition, using the limit definition of derivative, is very labor intensive. So we will spend some time trying to develop rules that will allow for this process to be much more efficient. So first of all, let's start with a little bit of notation. If the function is y equals f of x, then we have y prime or f prime, or df by dx, or df by dx, but with an f more separated. These two notations will be useful when the function's independent variable is very clearly stated and understood, whereas these other two notations have a big advantage of specifically stating what the independent variable here is, right? So this is specifically saying that you're taking a derivative of f with respect to x. Not time, not something else, but x in particular, okay? So these two last notations will be very useful in word problems that we'll see later today, as well as much later in applications like related rates. So first of all, let's take the simplest possible function we can think of, which is a constant function. So what if my function is just y equals 7? No matter what value for x I pick, y is always 7. Let's think about that as a graph. What does y equals 7 look like? Well, y equals 7 is a line, and in fact, it's a horizontal line. There it is. Graphically, the derivative is the slope of a tangent line to our graph. Here, it doesn't matter what point x I pick, the tangent line is the line itself, and the derivative is the slope of that line, which in this case is 0. So, since it doesn't matter what c is, so if c is 8 or 6 or whatever, it's always a horizontal line. A slope of a horizontal line will always be 0, so the derivative of a constant is always 0. Excellent. The second one is a power rule. Now this one I'm not going to derive from the definition, but this is where all the derivative rules come from. So what you should do is plug this into the limit definition of the derivative, simplify, open up the brackets, cancel out things that you can cancel out, compute the limit, and you will get the actual result. I'm not going to go through all this algebra, but I will give you the final result for the power rule, which is telling us how to compute derivatives of power functions. So anything x to power any n, this rule will work for. So the rule is that the power actually comes down to the front and gets reduced by 1. And this is true for all powers n. And it's truly true. This is the best rule because it's true for all powers n. N can be integers, n can be fractional powers, n can be negative. No matter what power I have here, the derivative of it can be taken using the power rule. The power rule is really powerful. Now, let's take a look at the next two. So the next two are sum and difference rule. The difference rule will work the same way, but with a minus in between. So the sum and difference rule tell us that in order to take a derivative of two summands, f plus g, I can just take derivatives of them separately. Okay, and the reason this works, again, you can derive it purely from the definition. I am going to motivate it a little bit from the graph and a little bit from algebra. The idea is, if I, let's say, have two functions, f of x and g of x, their sum is x's don't change, right? So if I were to compute the point on the graph that corresponds, for example, to this value of x, let me put the value here, right? What I would do is just add up the y values for my two functions. So this is just above 2, and this is a little bit higher. So I will get something like 5. So the point on my f plus g graph will be a point here. If I pick another value of x, I go through the exact same process of just adding up the height of f plus the height of g. Okay, so if I do this a little more carefully, I'm going to get a function just like this one, f plus g. And then remember that the derivative in its essence is just rise over run. It's just I'm taking the run over really, really small segment, okay? So for the derivative of f plus g, it's going to be rise, however much I manage to rise, over some fixed run. If I pick 2 points here, the x values here and here, notice that my x segment doesn't change. So the run for all of these functions is the same, but the rise is different. And the rise for f plus g is composed of the rise of f plus the rise of g. So I can break up this function over the denominator, and I'm going to end up with rise over round of f plus rise over round of g, which means I have a separate derivative of f and a separate derivative of g. The other way to write this rule, just to practice a little bit with notation, would be to say that f plus g prime is just f prime plus g prime. Okay? So if I have a sum, I can split them up and compute the derivative separately. And again, the same is true for the difference. So if I have f minus g all prime, it's the same as taking the derivatives of the two functions separately, which is very handy. The constant multiple rule is another really useful tool in computing derivatives. And this is just saying that if I do have some kind of constant inside my derivative, I can simply take that out and compute the derivative of only the function that is in fact dependent on x. Okay? So again, writing this in the prime notation, I will say that if I have c times f prime, I can take the constant c out and take a derivative of f only. And again, motivating this graphically just means that if I were to construct a graph here of, let's say, 2x, right? Nothing really happens to x's, but, so let's say this is going to be about 3. So this is approximately 2f of x. And then if I were to take some points on it, let's say the rise over run between these 2 points here and the 2 points on my original function, you notice that the run doesn't change. So this sort of denominator thing stays the same, but the rise now increases. So the rise over run can still be computed from the original function, but they've been now stretched out by this factor c. Okay, so these are some of the basic rules. Let's try to see how they actually apply to functions. So my favorite application on estimating the age of fetus growth, I showed you this formula last time. We approximated the derivative using this formula. We're now going to be able to compute it exactly using differentiation rules. So the first part is asking to calculate and interpret the derivative of L with respect to t, that's what this notation means, at different points in time, at 15, 20, and 30 weeks. Great. So this is my function L. It might be useful to just highlight where the actual variables occur, so the function's real nature stands out a little bit more. The function itself is just a cubic polynomial. Okay, so let's take a derivative of this thing. So first of all, I'm going to take the derivative of L with respect to time. That's where this notation is useful. It tells me very clearly what I'm taking in the derivative of with respect to what. And it's also telling me very clearly what the units should be, because the top is the units of L, which are in millimeters, and the bottom are the units of t, which are in weeks. So my answer will be in millimeters per week. Fantastic. Okay, so the other way to write this is, of course, to say this is L prime of t. And the verbal description of this would be that this is the rate of growth of the fetus, of the femur. I guess I can be more specific. Okay, so these are all the possible descriptions of this derivative here without the graphical one because we don't actually have the graph here. Fantastic. So I'm going to take a derivative of this. I'm going to do it very slowly because it's the first example we're doing. So the very first thing I'm going to do is just to rewrite the entire thing. There it is. And I'm taking the derivative of it. So I'm going to use the prime notation. So this whole thing primed. Now, the first thing to note here is that it's actually 3 separate pieces with a plus and minus in between and the derivative of that. So the sum and difference rule suggest that I can break this all apart and take derivatives of the separate pieces themselves. Okay? So the very first thing I can do here is just to say, let me move this out. It's just to say, okay, so this is the same as taking the derivative of the very first piece plus taking the derivative of the second piece minus taking the derivative of the third piece. Okay, and this is already much better because now everything's a little more compartmentalized. Okay, so now let's go through these one at a time. So this first thing that I'm taking a derivative of is just a constant. And remember, we just talked about a couple of slides ago, a derivative of a constant is just 0. So this is just 0. Plus, now let's take a look at this guy. So this is a constant times t. Going back to this slide, it says that if I have a constant times a function that I'm taking a derivative of, I can just take the constant out and take a derivative of just the function. Okay, so this again will simplify things quite a bit. I'm going to take out the constant 3.71 and take a derivative of just my function being just t. Great. Here it's the same thing. This whole thing is just a constant. So I can leave it alone or take it out, whichever way you prefer to think about this. And all I need to do is take a derivative of t cubed. That's fantastic news. The reason this is particularly great news is because the two things I have to take a derivative of are both functions that are power functions. T to power 1, and this guy is t to power 3. So I can apply my power rule. Remember, the power rule says that the power comes down and gets reduced by 1. Okay, so what am I going to have here? So this is equal to 3.71. The power comes down, which is 1, and gets reduced by 1 down to 0. Great. Now here I'm going to leave my ugly constant and take a derivative of t cubed. So the power 3 comes down and it gets reduced by 1 to t squared. And that's it. I'm done here. I can do a little bit more simplifying because I can notice that t to power 0, anything to power 0 is just 1. So this guy is actually just 1. So in fact, the derivative of t is just 1. So altogether here, I'm going to have 3.71 minus 6.33 times 10 to the negative 4 times 3t squared. And this is my derivative. Now that I've computed the derivative, let's get to the rest of this question, which is asking to not just compute the derivative for any value of t, but rather to figure out what are the exact numbers for 15, 20, and 30 weeks. Okay, so here's my derivative, same as the one on the previous slide. That's where I got this from. I have to compute this at these 3 different points. The notation for that, so if I had labeled this L prime of t, then what it's asking me to compute is L prime of 15, L prime of 20, and L prime of 30. But just so we're a little more used to this dl by dt notation, the way we denote it there will be dl by dt, and I have to compute it at t equals 15. So you do a really tall vertical bar, and then you write what point you're computing this at afterwards. And then I also have to compute this at 20 and at 30. Now, of course, the computational part is really straightforward because all I am doing is plugging 15, 20, and 30 into this derivative function, and I'm just getting a number answer in the end. Okay, so my numbers here, once I plug them in, would be 3.28, 2.95, and 2.00. Okay, now again, thinking back to units, this is where this notation is much more useful because this is saying these are the units of L over the units of T. So the units of L were millimeters, the units of T were weeks. So all of these have millimeters per week. Okay, fantastic. And part 2 of the question asks, does the rate of growth of a fetus increase or decrease with age? Okay, and we can see that the numbers are all positive, which means that the rate of growth is positive. So the fetus, femur, continues to in fact grow. However, first it grows pretty quickly, and then it grows a little bit slower because the numbers are smaller, and then it grows slower still. So it continues to grow, but the rate of growth slows down. Okay, so for part 2 of the question, we can say that continues to grow, but slower. Next up, let's talk about product rule. So we've seen how we can take derivatives of functions that are added together with constants, but what about two functions that are multiplied together? Okay, so here's what would have happened if the product rule was the same as the sum or quotient rule. So if I have the product of two functions, is that true that the derivative is the same as the product of the derivatives? Probably not if we're talking about this. So let's think about what a product can represent geometrically. If I say things like 3 times 5, how can you actually picture it visually? 3 times 5 means, let's say I took a plot of land 3 meters by 5 meters, and then 3 times 5 describes the entire area of that plot. So in this case, it's very useful to think about f times g as the actual area. So let's say I have myself some sort of rectangle in dimensions of f by g, and then in the sort of derivative manner, the whole point is that things are changing. It starts to grow in each dimension. And the question really is, how did those dimension changes influence the areas change? Okay, so this isn't going to be by any means a very rigorous argument for the product rule. In fact, it's going to be quite hand-wavy, but I'm just trying to give you some motivation and some intuition for what it is without really going into the very tedious computations, okay? So the idea is more or less that as the dimension of f changed, let's call this tiny little addition to it f prime. So it increased by some amount f prime, right? So this length here is f prime, and on the g side we can think of that as a small change in g, so g prime. Okay, and now let's think about what are the areas. So this area is still f times g because it's length times width. Now what about the area of this little rectangle? Well, the length times width here, now the width is f prime and the length is still g, right? So this guy is f prime g. And the same logic applies to this little rectangle where the width is still f, but the length now is g prime. So this guy is f times g prime, whereas this little corner guy is f prime g prime. Now, if my changes were teeny tiny, like they're supposed to be when I'm talking about derivatives, because the limit is supposed to go to 0, this little corner here, I'm multiplying a teeny tiny number by another teeny tiny number. So this corner here can essentially be negligible. Negligible. And so what the area has changed by, so what has been the change in my overall area? Well, my area used to be that, and now it's this whole thing, and I'm counting this as negligible. So the change that I've introduced is the area of the two red rectangles, which are f prime g and f g prime. Okay, now once again, this is by no means a rigorous argument, but this is just to remind you that the product rule is not as easy as just sort of distributing the derivatives in. Product rule talks about a different dimensions of function change. So it's going to be quite a bit more complicated than the sum and product rule that we've seen before. Okay, so in product rule, if I have f times g, then I have to first take a derivative of the function f, leave g alone, and then leave f alone, take the derivative of g. Let's see how that works in an example. So here's our first one. Find the derivative of 3x times x plus 1. Okay, so here it's a clear product rule. This is my first function, let's call it f, and this is my second function, let's call it g. So the product rule says I'm going to take a derivative of the first function first, so 3x prime, and leave the second one be, plus I'm going to leave the first one alone and take a derivative of the second one. Okay, so this is just what the first step of the product rule will give me. Now I actually have to go ahead and take those derivatives. So what is the derivative of 3x? Well, the constant I can just leave, and then I have to take a derivative of x, which is just 1. It's 1 times x to power 0, which is just 1. And then times this x plus 1 bracket, and then I have 3x, and now I need to take a derivative of x plus 1. Now, once I have a sum, I can take a derivative of each one of them separately. So it's a derivative of x plus a derivative of 1. Okay, let me write this out for one more time. So this is 3x plus 1 plus 3x. The derivative of x is once again just 1. The derivative of 1 is a constant, so it's 0. Okay, I can open up the brackets now and simplify this. That will be fine too. So 3x plus 3 plus 3x. So overall I get 6x plus 3, and that's my final answer for the derivative. Okay, so this is how one applies the product rule. I strongly encourage you to actually open up the brackets of this thing and do it the different way, just to practice a little bit more with the other differentiation rules.
A few more applications of the exact same rule, but within an application, and therefore needing to provide an interpretation of the result. So we've seen this example before, melting Arctic sea ice. We have seen this with the graph of a function. This is now the actual function that has been fitted to the data collected. So this is showing the amount of ice in millions of square kilometers, where t is the number of years since 1980. And the first part of the question asks us to find s prime of 20 and s prime of 30. So the derivative of this function at the point 20 and 30 years after 1980. Now, first of all, I'm going to have to find the general derivative, so s prime of t in general. And then once I have that expression, I can put t equals 20 and t equals 30 into it in order to actually calculate those values, right? So these are not actually disjoint parts of the question. We are going to have to do some overhead work first and then actually evaluate them at those numbers. So just like in examples before, what I'm going to do, because this is one of the first ones, I'm going to go through a step-by-step calculation. As you get more proficient with these calculations of derivatives, you will not have to actually go through so many intermediate steps. But for now, and because I am actually pointing out what the possible ways to interpret this is, I'm going to do a very detailed job of it. Okay, so we start off by saying we would like to take a derivative of this entire expression, and then one of the first rules that we can apply is the fact that the derivative of the sum is the sum of the derivatives, so we can take each one of these terms separately and differentiate them one at a time. And now that I have that, I can start applying other differentiation rules. So this first part here is a constant. The derivative of a constant is 0. The second part here has a constant times the actual variable that we're differentiating with respect to. So I'm going to keep the constant and then take a derivative of the remaining variable. Now this is t to the power 1, and so we're going to apply the power rule. The power 1 comes down, and the 1 gets subtracted from the power. So what I'm going to have is 1 times t to the power 0. Now again, as you practice more and more often, you will simply get used to the fact that a constant times t will produce a derivative that is just that constant. For the second half here, what I'm going to have is the constant, and then I need to take a derivative of t squared. I'm going to bring the power down and subtract 1 from the power. So 2t to the power 1. I can now bring everything back together and simplify my terms. So once again, this is simply just 1, and I don't need to include 1 in the power if that's the only thing in there. So altogether I have 0.023 minus, and now I can actually multiply these two numbers together to get 0.008t. This is the expression for my derivative now. So if I would like to calculate the derivative of 20, I simply plug in t equals 20 into this expression. And what am I going to get in this case? So here I will have 0.023 minus 0.008 times 20. And this will result in a number minus 0.137. Okay, I'm not going to worry about units yet. I'm just going to plug in both of the numbers in to calculate, basically so I can get rid of actual calculations. So here I plug in 30 into this expression. What am I going to get? 0.023 minus 0.008 times 30. And this will give me a number minus 0.217. So I have my actual numbers. Because the function given to me in the context comes with units, I would like to actually include units as part of my answer here. So the original function was in millions of square kilometers the derivative is the rate of change with respect to the independent variable, so with respect to years. So what we have is millions of square kilometers per year for each one of these two derivative values. The other thing that I would like to point out here is the fact that you calculate the derivative first and then you plug in a number. If I did it in the other order, it wouldn't quite make sense. If I plug in the number into here, I will be calculating s of 20, not s prime of 20. And then s of 20 will turn out to be a number whose derivative is of course going to be 0. You have to calculate the derivative as a function first, and then plug in the value at which you're interested in the actual instantaneous rate of change. That's the only way that you will produce numbers that are meaningful. So now what do we have? We have the negative number here, minus 0.137, and a negative number here, minus 0.217. So what trend do we see in the derivative? Well, the derivative was negative and it's staying negative, but it's actually getting more negative. This number is more negative than this number. So the trend that we're seeing is the derivative is becoming more negative. Let's write that down. Derivative is becoming more negative, but this is a very straightforward mathematical observation. What about in terms of actual context? What does that mean? Negative means the function is decreasing, right? Remember that the derivative is the slope of a tangent line. And if the slope is negative, it means that the tangent line looks like this, which means that no matter what way the function goes, it will be at that point decreasing. It will be pointing downwards because the actual tangent line is pointing downwards. So that means that the ice is indeed melting, and it's actually melting at a faster rate. Again, remember that the derivative represents the rate of change. So this rate is more negative than this rate, which means that the actual melting is happening faster. So we can also write that down. Ice is melting faster. And again, you can think of melting here as the fact that the function is decreasing, and the function represents the total amount of ice, which means that the decreasing amount of ice will actually correspond to its melting. Take a look at this slide and then a slide from a few lectures ago where we analyzed the exact same function with the graph in order to actually compare what we found there for these values and what we found here to see how the approximations from the graph and the intuition from the graph compares to the algebraic approach for the exact same function. For our next example, we're going to examine the following data in this following graph. It shows the number of cases of multiple sclerosis in hundreds of thousands as a function of latitude that is based on the data collected in 3 different US communities at different latitudes. The red dots on the graph here correspond to the actual data collected, and the black curve corresponds to the best fitting quadratic that is given by this formula. So in this example, we have both the graph and the actual formulaic representation of the best fitting function to it. First of all, before we dive into the actual question parts, let's examine what this is saying. What is latitude? If you think of the Earth, a big sphere, yes, it is indeed round. It has North Pole, South Pole, and an equator. Equator is latitude 0, North Pole is latitude 90. So the latitude increases from equator to the North Pole, with Abbotsford being approximately 49. So we're just under halfway up between the equator and the North Pole. So this is increasing as we move towards the North Pole. And what we're seeing on the graph is as the latitude goes from low or like mid-20s here to high 40s, the number of cases of multiple sclerosis seem to increase, right? While this might not be necessarily the function, it's the best fitting quadratic, but it could have been the best fitting, cubic and whatnot. So this function, of course, doesn't model every single point of the data perfectly, but we certainly see an increasing trend in the data points that we're seeing. And hypothesis is that the higher latitude results in smaller exposure to the sun, because it's closer to the North Pole, the days are shorter, and therefore less vitamin D exposure, which then results in higher number of cases of the multiple sclerosis. So there's some serious data collection and investigations going on to figure out whether this hypothesis is true or not. What we have here is the actual data, the function that describes it, and then we're asked to find and interpret the various derivative values of it. So as in the question before, I'm noticing that I have to calculate the derivative of two different points for x that corresponds to the latitude. So before I do that, I'm going to have to calculate the derivative function in general. So p prime of x. Here's my function. So I'm not going to include every single step here. We've seen enough of very detailed calculations. Let me skip a few steps. If I'm going to take the derivative of this, I know that the derivative of constant is 0, so this will simply go away. I've already seen enough examples to know that the derivative of a constant times the variable is going to be simply the constant itself, so minus 30.8. And then what's going to happen here is I'm going to keep the constant and apply the power rule to x squared. The power rule will come down, so it'll be 0.5 times 2, which is 1. And then I'm going to subtract 1 from the power. So this will result in plus 1 times x, or simply x. So now I can calculate these two values by plugging in 40 and 45 directly into my derivative function. So if I plug in 40, I'm going to see that I get 9.2. If I plug in 45, I'm going to get 14.2. What are the units of these derivatives? So remember the notation dp by dx here, the rise over run, might be a little bit more conducive to thinking about units. The p units are cases in hundreds, thousands, and the x units is the degrees of latitude. So this will be number of cases, again in hundreds, thousands, but I'm not going to write that down, per latitude. Cases per latitude. Since we're given the graph of this function, let's also think about what these numbers represent on the graph, and does our graphical visualization support the fact that these numbers seem to be growing with latitude. So at 40, I'm going to look at this here. The derivative, remember, represents the slope of the tangent at that point. So if I draw a tangent line here, the slope of it at 40 should be the value of the derivative, so 9.2. If I draw the derivative at 45, the slope should be 14.2, and what I should be seeing on the graph is that my slope is in fact steeper. And indeed, it does look like it. It looks like the function is increasing, and it's increasing faster. Okay, so the slope is getting steeper and steeper as we go along. Okay, so maybe I will label this as slope 9.2 and this as slope 14.2. So the trend that I'm noticing is that cases increase at a faster rate at higher latitudes. Okay, so not only is the entire function increasing, the rate at which the cases are increasing is also itself getting faster. Okay, now whether or not this hypothesis is in fact supported by more recent or more detailed data is something you can look up. But again, these are the types of things that we can do when we discuss the graph, the function, and its derivative. In your notes, you will also find this worksheet that walks you through more examples of looking for the derivative analytically, as well as connecting it to the graphical representation of these concepts. So I strongly encourage you to actually work through this worksheet for more practice.